Before starting section 7, digital control emulating analog design, let us review the sample data system. So we have here our process, which is continuous time. We have the analog to digital conversion. Here we have the digital to analog conversion with the zero order hold mechanism. And of course here we have our digital controller, and here we have the set point and the control error. So here we have a minus and a plus. This is here the process value that is controlled. So in this section we'll focus on digital control that emulates analog design. So what do we mean by that? Well, we start with P of S, and what we'll do is design a C of S. This will be our analog design, and what we'll then do, and we'll use a sample period TS here and a discretization method, which is probably matched poles, matched zeros. This is the best way to go, and we obtain a digital controller, and this digital controller emulates the analog design, right? And we will see that if TS is small enough, and we have to say small with respect of course to the main time constant, well, this will work rather well. But if TS is starting to grow, right, then we can expect problems, and this is because we are not taking into account the zero order hold mechanism. So what we'll see in a tutorial example, that if we take another way and we first discretize the process, but we do it in a smart way, in the sense that we're taking into account the zero order hold mechanism, we obtain an equivalent description that takes into account this zero order hold mechanism. And then if we do a design based on this description, we will obtain a C of Z over here, well, that you can implement on the actual system like here, but you will see here that the performance specifications will be as expected even when T of S, the sampling period, is growing, and this is simply because we have taken into account the zero order hold mechanism. The simplest and probably cheapest and most straightforward digital control is to do an analog design and obtain a digital controller with a short sampling interval. So by obtaining a digital controller, we mean that we have to obtain a discrete time equivalent description of this analog controller. The analog controller is emulated more accurately if the sampling rate is high, so if the sampling period is short. This is because the digital controller that is emulating the analog controller operates upon the samples that are available and has no knowledge of the signal history since the last sample. So it is important that the sampling rate is much higher than the frequency band of the signals. The observed digital signal is delayed by half a sample period on average if you compare with the continuous time signal, and this is because of the zero order hold mechanism. This delay will of course be introducing a phase lag. The phase margin will be lower as expected, and the control performance will of course deteriorate. Well, this performance deterioration will be worsening the higher TS, the higher the sampling period. We have seen that the choice of the sampling frequency is very important, and this sampling frequency is usually based on the bandwidth of the controller, process or closed loop system. Usually the bandwidth of the closed loop system is the largest, and it is known from the specifications in the control design. Well, reasonable sampling rates are 10 to 30 times the closed loop bandwidth. We have seen previously that the sampling rate is linked to the bandwidth frequency by this relation, which is of course a rule of thumb. Well, in the time domain, you can also say that per rise time you should have 4 to 10 samples. In theory, the higher the sampling rate, the better the emulation, right? If TS is small, then well, your digital controller will emulate the analog design in a better way. But of course, if you decrease TS, well, you also have to kind of increase the resolution of your data acquisition card, because if you increase TS, you will see smaller variations, and in order to see these smaller variations, you need a better resolution. This means a smaller quantization step, so a higher number of bits in the analog to digital conversion, so a higher price. So we see also, and we've seen this in the implementation of the PID controller, that when TS becomes very small, well, you can expect numerical problems in the implementation of control algorithms. Well, this is the design procedure if you want to do digital control emulating analog design. Well, of course, you should come up first with an analog controller, so you should designing. This will be the C of S, and then you have to discretize the controller and obtain C of Z, and this will be for a given sampling period. Well, to discretize this analog controller, well, best you should use the match pole 0 method, but you can also use numerical integration method. So for instance, Euler backward difference or the trapezoidal approximation method. Once you have the digital controller, you should perform computer simulation and check its performance. So you should simulate this digital controller on the continuous time system and add, well, analog to digital transition and digital to analog transition. So you should use a rate transition, and you should take into account the zero order hold mechanism. I will show you how to do this in Simulink. We will see that this will allow you to check also inter-sample behavior. Once you have done this computer simulation, you can check the performance and see if your TS is, well, appropriate in obtaining a performance that is similar to the one that you were expecting with your analog controller. If this is not the case, well, you should adapt the sampling period, so you'll have to decrease the sampling period. So you'll have to go back to step 2, discretize the controller with this new TS, and again do the computer simulation, check performance, and you do this until you have an adequate performance. In practice, that the performance with your digital controller is the same as the performance with your analog. Well, not the same, but very similar. Here you have an example of such a simulation of a sample data system. It is applied here to the tutorial example that we'll use in this section. So what you have over here is the process that we'll be using, and you can see that we are kind of emulating the zero order hold mechanism using this block. It is very important that you put the appropriate sampling period over here. So here we have the digital to analog conversion, and well, this is the continuous time process, and after the process we have of course the analog to digital conversion, and this can be implemented using a rate transition. Again, do not forget to set the appropriate sampling time over here, right? So this will allow us to simulate our digital controller on the actual continuous time system, taking into account the zero order hold mechanism. And as you can see, I can check intersample behavior. At the output of the rate transition, I will have the output at the sampling instance, but if I take this signal over here, I will have the behavior of the system even between sampling instances. In the rest of the course, we'll be using a process that is this one over here, and I want to show you where it's coming from. So it's drawn from the book Franklin and Powell, Digital Control of Dynamic Systems, from 1981. The reference that you will see at the beginning of the course is a more recent reference. The process describes the positioning of an antenna, right, in rotation using a DC drive motor. So what we'll use is the second law of Newton in rotation. So you have, well, the moment of inertia times the angular acceleration is equal to the sum of torques, right? So here you'll have the net torque, you'll have the disturbance torque, and you'll have a friction torque, and this one you can write as, well, a damping factor times the angular speed. So you end up with this equation over here. If we divide by c, right, we obtain this equation here, and you can compute that this is expressed in seconds. This will express a time constant. What we'll use as input is the net torque over this c to make everything easy from a notation point of view, and this, well, disturbance torque divided by c will be the load disturbance, and we have called it, I think, W at the beginning of the course, but it's sometimes also notated like this. If we go to the Laplace domain and we look at the transfer function between the input x and the angle of rotation, this is the transfer function that you obtain, and in our case, well, t will be 10 seconds. Well, as we have seen, the process that we have to control is this one with t is equal to 10 seconds, right? And we have to design a controller C of S, and what we'll have to do is to achieve a settling time TS that is approximately 10 seconds and an overshoot that is approximately 17%. So what we'll do is use a lead lag controller. This is a type of controller that you've also used in last year's course of Fundamentals of Control Theory. And what we'll do is use a controller of the type TS plus 1 over alpha S plus 1, where alpha has to be determined and then times a gain, and where the gain has to be determined. As you can see here, this 0 in the controller will cancel out the pole here in the process. We can do this because t is positive, so we have a stable pole that is cancelled. We will see in next year's course practical process control that this is not really necessarily a good strategy if you're in the presence of a load disturbance, WT, or as we sometimes write it, DL, because the zero in the controller will prevent you from, well, efficiently rejecting this load disturbance. We'll come back to that later in the course of practical process control. So remember that we cancel the stable pole of the process using this lead lag controller. So the loop gain, which is process times controller, will be Kc divided by S times alpha S plus 1, right? So if we write L of S over 1 plus L of S, which is the closed loop transfer function from reference signal, so from set point to controlled output signal, what we have is this transfer function over here. So you can rewrite it as follows, and well, you can see that you can write the transfer function as a second order system with complex conjugate poles. So 1 over alpha is 2 times zeta omega n, and Kc over alpha is omega n, the natural frequency, squared. Remember that an overshoot of 17%, we've seen this previously, corresponds to a damping ratio of 0.5, and the settling time should be around 10 seconds. And well, we've seen that the settling time is approximately 5 divided by the real part of the complex conjugate poles, and this real part is zeta over omega n. This is what we've called previously sigma, right? So if zeta is equal to 0.5, you can rewrite this as 10 over omega n. If you want a TS of 10 seconds, then you have zeta is equal to 0.5 and omega n is equal to 1 radian per second, right? So 2 zeta omega n will be 1, and omega n squared is 1 as well. So you can see from this equality, okay, 1 over alpha is equal to 1, that we need to take alpha is equal to 1. And if alpha is equal to 1, well, you need to take Kc is equal to 1. So we have now our controller that meets the specifications, and we have found values for alpha and Kc. We can now implement all this in Matlab. So this is the implementation for the system. This is the implementation for the controller. You can see over here that this is T, so this one will cancel out with this one, and this one over here is alpha. So the closed loop system is like this. So let's call this, well, PV, SP, and MV. Okay, so what we want to simulate is the transfer function from set point to process value, and from set point to, well, manipulated value or input of the system. And you can use this feedback command in Matlab, and well, if you implement feedback sys1 sys2, right, this is really what you're going to implement, sys1 sys2, and with a negative feedback over here. Okay, so sys2 is the one that is in the feedback part. So if we have a look for the transfer function from set point to PV, what you have to put in sys1 is P times C, and in the feedback part, well, you have A1. This is precisely what we have over here. And if you want the transfer function from set point to MV, sys1 in this case will be the controller, and in the feedback part, so this is the output now, in the feedback part you have the process. So this is how you can construct the two relevant transfer functions. So what you see here is the closed loop response to a step at the set point. You can see here that the settling time is indeed approximately 10 seconds and that the overshoot is around 17%. And of course you should also have a look at the output of the controller, so the controller energy, and this is the plot that you obtain. What we now want to do is to emulate our analog design and in such a way obtain a digital controller. So we'll start from the controller that we had obtained, which is TS plus 1 alpha S plus 1 times Kc, and here Kc is equal to 1 and alpha is equal to 1. So we'll use the mapped poles and zeros method. Okay, so the numerator here we have a 0 and minus 1 over t, and alpha is equal to 1. Here we have a pole in minus 1. So the discrete 0 will be the exponential of ts, the continuous time 0, and this will result in this 0 over here. The discrete pole will be e to exponential of ts times the continuous pole, so this will result in, remember that this is here the continuous pole and this is equal to the continuous 0, and this will result in a pole in the exponential of minus ts. We have a gain here, and the gain is adjusted in such a way that the static gain of this controller corresponds to the static gain of the original controller. You can very easily see that the static gain of this controller is 1. You simply replace S by 0, Kc by 1 and alpha by 1, and indeed you see that this static gain is 1. And in order to have a static gain that is 1 over here, well, you need to compute the static gain of this controller, right? Well, here we have to replace Z by 1. Right, so the static gain is this expression, and in order to have a static gain of 1, well, you need to make sure that this gain here is the inverse of this one. So this is here the gain in discrete time of my mapped poles and zeros digital version of my original controller. If we now replace ts by 1 and t by 10, this is the controller that you obtain. So we have now our digital controller C of Z. There are now two ways to test this controller. The first way is to use Simulink, as I've shown you before, and the advantage is that you'll be able to also look at the inter-sample behavior. Another way is to test your controller in Matlab, and then you'll need a description of the system that will be including the zero order halt mechanism. So you'll be able to simulate the system at the sampling instance, but what you will not have is the inter-sample behavior. We are now looking for the zero order halt equivalent description of our system. and we had seen that you can obtain it as follows. So here you have the original continuous time system. This is how you take into account the zero order halt, right? And we had seen that you could rewrite this differently, and you could also obtain it by considering that this zero order halt equivalent is exactly also the step invariant equivalent description of this process, right? So here you have the step response in the Laplace domain. The inverse Laplace response is taken, so this one over here is the step response. We sample this step response, we take its z transform and then multiply by 1 minus z minus 1. So what we need to do to take the inverse Laplace transform is to do the partial fraction expansion, and this quantity over here can be rewritten as minus t u of t plus t u of t plus t exponential of minus t over the time constant u of t. And then we have to sample. If we sample, we'll end up with the following discrete time signal: minus t u of k plus ts k u of k plus t exponential of minus ts over t to the power k u of k. And if you take the z transform of this one, this is what you obtain, right? So these will cancel out. This one will cancel out with this one, and there will be a z minus 1 over here. And if you put everything under the same denominator, z minus 1 will come from this one, and this one over here will come from this term. But if you put everything under the same denominator, this is what you will obtain, where a and b are constants that of course depend on the time constant and on the sampling period. This is the zero order halt equivalent description of our process with the exact expressions of a and b as a function of the sampling period and the time constant. So if we replace ts by 1 and t by 10 in seconds, well, this is the equivalent description that we obtain for the process. We had already obtained this expression over here for the controller. We will see that to obtain this expression here, we could also use the Matlab command C2D, right? So this will obtain directly this expression, and I will show you now that the exact expression as a function of ts and t can also be obtained by Matlab using the symbolic toolbox. This is the way to go in Matlab using the symbolic toolbox. So you first have to define all the variables as symbolic. This is the process, this is the step response in the Laplace domain. You take the process times 1 over s. To obtain the step response in the time domain, you have to take the inverse Laplace transform, and here you replace t by nts, so this is sampling, and here we have a discrete time sequence. Once you have it, you have to compute the z transform and multiply by z minus 1 over z, and all the rest is just a matter of doing simplification, collecting things in z and obtaining the numerator and denominator. So what you obtain is this zero order halt equivalent description of the process that we have found in the slides by hand calculation, and where a and b depend on the sampling period and the time constant. Well, to help you explain things visually, this is a slide that might help. So this is the digital controller, and well, you can simulate the sampled data system in Simulink. So you'll have to use the continuous time transfer function, the zero order hold block, and here the rate transition, and you'll be able to obtain, well, the output at the sampling instance, but also the inter-sample behavior. If you want to work in Matlab, then you'll have to look at the process from this input over here, which is x of k, and this output y of k. So we'll have to rework this in order to obtain the zero order hold equivalent description of the process. It will take into account the hold mechanism, which is a zero order hold in our case. But of course, what you will not have if you work with Matlab and, well, this process in the loop with this controller, well, you will never have the inter-sample behavior. Well, in order to rework this control loop, what we'll do is replace the digital to analog conversion by an ideal digital to analog conversion, and we'll do the same for the analog to digital conversion. Of course, for the digital to analog conversion, since we replace it by an ideal element, well, we have to kind of take into account the zero order hold by modifying our process. And this is the way we modify the process. This is going to take into account the zero order hold mechanism. Well, from the perspective of the controller, this interface and this continuous time process that takes into account the zero order hold mechanism can be replaced by a process which is the zero order hold equivalent or the step invariant equivalent. So in Matlab, what we can do is simulate the system with our digital controller, and this one is here the zero order hold equivalent description of the process. So this can be done in Matlab. Sometimes it's easier to work in Matlab, but remember that the downside is that we do not have access to the intersample behavior. Well, this is the way to go in Matlab. So this is the continuous time description that we had before. We have here a sampling period that is 1 second, but you will see that in the simulations you can very easily change this and see what is the impact of TS. So for the process we need, of course, the zero order hold equivalent description, so we can use the command C2D. You do not even have to put the argument, because if you do not use an argument, it's the ZOH discretization method that is chosen automatically. So this is what you had seen here also when we had done the continuous time design. So now we need a description in discrete time, and remember that we had used a matched pole and zero method. So this is why we use here this argument. So we choose to do it in Matlab using the C2D command, but we could also use the expressions that we had found for the discrete implementation of the controller using hand calculation. So we have a description of the process in discrete time, and we have a description of the controller in discrete time. So what we can do is compute the two relevant transfer functions, the one that goes from the set point to PV, or from R to Y, and here from S P set point to MV, the manipulated value, or from R to X. And then we can have a look at the step responses. So here we have the output step response in closed loop. In blue here we have the continuous time response that we had obtained previously, and here you see the discrete time response with TS increasing. So we're starting from TS is equal to 0.1, then we take TS is equal to 0.3, and then finally TS is equal to 1. And we can clearly see that using this digital control emulating analog design, well, everything seems to be okay when TS is sufficiently small, but as TS increases, you can clearly see, well, that, well, for this TS is equal to 1, for instance, that the specifications are no longer met. And this is kind of obvious because we did not take into account the zero order hold mechanism. As usual, we should also look at the control energy, and we have the corresponding responses over here. As you can see, and as you could see in the previous responses, we do not have the intersample behavior because we are working in Matlab. If you do the simulation in Simulink, you'll also have access to the intersample behavior. Well, if you do the simulation in Simulink, you have to do it as follows. I've shown you this before. So here you have the process with the zero order hold mechanism and the rate transition, and here you have the controller, and if you click, it's the controller that we have obtained using this matched pole and zero method. Again, make sure that the sampling time is the one that you have decided upon, and in this case it's TS, a sampling period that is 1 second. So we can now simulate the system and have a look at the response. And as you can see, the response is exactly the same. You can see that indeed the sampling period is 1 second, but in addition to the response at the sampling instance, you also have the intersample behavior, and as I've told you before, you should always check it. So really, Simulink is the way to go. We can see here that for TS sufficiently small, the specifications are met. So we have a zeta of approximately 0.5 and a natural frequency of 1 radians per second. Well, let us find a reasonable bound for the sampling period by considering the rule of thumb that we had used before, that the sampling frequency is approximately 20 times the bandwidth of the system. So 20 times the bandwidth of the system will approximate it by approximately 20 times the natural frequency in closed loop, which is not the same, of course. This is here 2 pi over TS, right? By the way, we have imposed omega n to be 1, so this is why we have approximately 20. So from this relation we can see that, well, a reasonable bound is TS is equal to pi over 10, which is 0.3 seconds. So TS smaller or equal to 0.3 seconds is a reasonable bound according to this rule. Let's check this. So the rule that we had obtained, or the reasonable bound, is this one. You can see clearly that, well, you should choose TS, well, a lot smaller than 0.3 seconds, because if you choose 0.3 seconds, you can see over here that there is already a large influence on the overshoot. But you can clearly see that if you choose TS larger than 0.3 seconds, so for instance TS is equal to 1 second, then the effects become dramatic. we know the process description P of Z, and we have the controller. So what we can compute are the poles in closed loop for, well, TS is equal to 0.1, 0.3 and 1. So if we compute those poles and we place this on this diagram, this is what you obtain. And as I said, this is TS is equal to 0.1, TS is equal to 0.3, and this is TS is equal to 1. Remember that we had imposed a zeta of 0.5, so we should be on this curve over here, and this is not the case clearly. Okay, so here we see that we are closer to zeta is equal to 0.2, so the damping is not as good as expected, and this is, well, the result of the zero order hold mechanism that has introduced a delay of roughly TS over 2. So the phase margin is much smaller than expected. With an omega n is equal to 1 and a TS is equal to 1, well, we can compute the equivalent m, and we know that omega n is equal to pi over TS, so times m, of course, here. So m is equal to omega n TS over pi. So this is 1 times 1 divided by pi, so this is roughly 0.3. So we would expect a pole that is over here, right? So what we'll do next is do so-called direct digital design. So we'll work directly in the discrete time domain, and we'll do pole placement and place the pole over here. So in summary, as we have seen in the diagram, for TS is equal to 1, the roots of the equivalent discrete time system are actually near to zeta is equal to 0.2 and m is equal to 0.3. So the accuracy of the approximation is not adequate. The damping is not as good as expected. And this is because of this zero order hold reconstruction that has not been taken into account. This zero order hold reconstruction introduces a delay of roughly TS over 2, right? So this will dramatically, in this case, decrease the phase margin. And you can see, of course, that the influence of this zero order hold mechanism increases with increasing TS. Well, we had seen that using this rule of thumb that Fs is approximately 20 times the bandwidth frequency, we had obtained a TS that should be smaller than 0.3 seconds. If TS is above that value, then clearly, well, we should abandon the idea of using digital control emulating analog design, and what we should do is direct digital design. So for that we need a description that includes the hold process. So here is zero order hold, and this is this description that we had obtained previously. So when you do a direct digital design, this means that you work with a controller that is designed directly in the Z domain. And here again we'll use a lead lag system with a gain but in the Z domain, and we'll use the same idea as in the analog design. We'll cancel the pole of the system, the one that corresponds to the time constant in continuous time of t. So we have a 0 here that will cancel out this pole. We have a cancelling of a pole by a 0 of the controller, so we should check that we do not go against internal stability, and everything is okay if this pole here is inside the unit circle. If you check, we have t constant, time constant is 10 and ts is 1 second, then you can see that the cancelled pole is in 0.9. So indeed it is inside the unit circle. So we now have to determine the gain of the controller and this alpha over here. The idea is to place a closed loop pole in beta plus gamma j, right? And there will be also one that is mirrored on the other side of the real axis, so we'll have two poles, right? And well, since we're here on this line that corresponds to zeta is equal to 0.5 and that omega n is equal to 1 and ts is equal to 1, have led to m is equal to 0.3. This is where we want the pole. So we have beta plus minus gamma j is approximately equal to 0.43 plus minus 0.45 j. We had seen that the loop gain P times C was, because there is a pole zero cancellation, Kc Az plus B over Z minus 1 times Z minus alpha. So what we can do is compute the closed loop transfer function from a reference signal set point to controlled output, and this is PC over 1 plus PC or L over 1 plus L, and this is what you obtain. And if you rework the denominator, this is what you obtain. Remember that the idea is to place the poles in beta plus minus gamma j, so the denominator will be Z minus beta minus gamma j times Z minus beta plus gamma j. And if you compute this, this will give Z square minus 2 beta Z plus beta square plus gamma square. Okay, beta and gamma are known. Okay, we even know the values, right? We have seen it from the diagram, and it's 0.43 plus minus 0.45 j. So this is beta and this will be gamma. So what we can now do is solve a system of equations with two equations and two unknowns. The unknowns are alpha and Kc, right? And you can see from this equation that Kc is obtained rather easily, right? Alpha plus Kcb is equal to beta square plus gamma square, so this is what it yields. And if you inject this one in here, right, and then you set this equal to 2 beta, you can isolate alpha. But anyway, you can see that you can obtain alpha and Kc as a function of the real part and the imaginary part of the poles. So with Ts is equal to 1, we had already obtained the zero order Holt equivalent description of the system. Here we want a damping ratio of 0.5. We had seen that the setting time of 10 seconds had led to omega n is equal to 1. With TS is equal to 1. This corresponds to an M, which is 1 times 1 divided by pi, so approximately 0.3. So if you look in this Z grid, okay, and you look at the place where you have M is equal to 0.3 and zeta is equal to 0.5, you can locate the desired closed loop poles for our direct digital design. And beta is equal to 0.43, gamma is equal to 0.45, as we had mentioned before. Then you can compute Kc and you can compute alpha. Okay, this one here is the 0 that will cancel out this pole over here. So we have obtained our digital controller after a direct digital design. So what you can now do is test it, and in this case we'll test it only in Matlab. So here's the Matlab code that is there for your information. So here we have the zero order hold equivalent of our original system. This time we have used the expressions that we have found by hand calculations. Equivalently, we could have used the C2D command. This is the matched zero pole discretization that we had obtained previously, and now we're going to compare it with a direct digital design. So these come from the two poles that we have selected in our Z grid, right? And now you can compute alpha and the gain of the controller. So this is here Kc. If you plug that in the transfer function, well, you obtain the controller that results from a direct digital design. You can now have a look at the closed loop transfer functions. Well, the closed loop transfer function that results from a direct digital design and one that results from a matched zero pole discretization, and you can compare. So here you see the output step responses. So the continuous time response with the continuous time controller, it serves as a reference. You can see here that we have an overshoot of roughly 17% and a settling time of roughly 10 seconds. If we use a digital controller that comes from a matched design, you have the response in green. This is for a TS sampling period of 1 second, and clearly the specifications are no longer met. You can see that the damping in closed loop is not as good as expected. But you can also see that if you use a controller, a digital controller that results from the direct digital design, again with the same sampling period of TS is equal to 1 second, well, you obtain very good results. The specifications are met. As you can see, we have an overshoot of roughly 17%, and well, the settling time is also approximately 10 seconds. And here you obtain the equivalent responses as far as the control energy is concerned. As a conclusion, we can see that if you choose TS larger than what is advocated by these rules of thumb, a matched design will not give good results, and this is because the zero order hold mechanism is not taken into account. For those values of TS that are larger than advocated by the rules of thumb, you should do a direct digital design, and this will take into account the zero order hold mechanism.